now I want to go through a proof of part 2 of Theorem 7. And again, I'm not going to go through all of the theorems in the notes in lecture video form. There's a lot you can get more efficiently by reading, but every time there's kind of a new technique coming up that we haven't necessarily used before, I want to talk about it. So this one is called Transitivity of Inclusion, and it's another one of these transitivity things. Transitivity meaning you've got a relation operator looking thing, where when one thing is related to another and that's then related to a third thing, then the first thing is related to the third thing. So this is one of those. If A is a subset of B and B is a subset of C, then A is a subset of C. So I'm going to write the proof, and kind of on the side here, I'm going to keep a description of my goals. So what I'm putting on the side here is kind of scratch work. This would be something that maybe I keep on a piece of scratch paper while I'm working on my proof, but I would definitely not include it in my final proof. So this part is secret, and I wouldn't normally show it, but I'm showing it because I'm trying to show you the thought process. So, okay. The first goal is the overall theorem, right? I'm trying to prove A subset B and B subset C implies A subset C. That's my initial goal. And I'm going to keep updating my goal as I go down and try to fill out the proof. So my initial goal is an implication. How do I prove an implication? Well, going back to our treatment of logic, to prove an implication, assume the hypothesis and prove the conclusion. So assume that A is a subset of B and B is a subset of C. And now my goal updates. The goal is now to prove the conclusion. So this is the goal I now have in mind. Prove that A is a subset of C. But I can rewrite this using the definition of subset, the definition of inclusion. My goal is to prove that for all Z, if Z is in A, then Z is in C. So my goal is to prove that every element of A is an element of C. So how do I prove a universal? To prove a universal, it's a universal generalization kind of argument that I should go for. So that means consider any Z, and then leaving Z arbitrary, try to prove that if Z is in A, then Z is in C. So I'm going to write it one way, and then I'm going to erase it and show you how people would normally write it, actually. So here's the universal generalization argument. Consider any Z. Then I'm supposed to do a bunch of work to try to prove this, right? So as soon as I say consider any Z, my goal updates to this. I'm now trying to prove Z in A implies Z is in C. So how do I prove an implication? Again, assume the hypothesis and prove the conclusion. So now I'm going to say, assume Z is in A. Then I will try to do a bunch of work and prove that Z is in C, right? And then when that's done, I will have proven this implication. And then when that's done, I will have proven the for all Z statement that I wanted. Normally, the way that people do this is they make it a little bit more efficient by merging these two sentences. So instead of consider any Z, where Z is just anything, now assume Z is in A, instead they'll say consider any Z that is in A. So consider any Z such that Z is in A, or even shorter, consider any Z in A. So that's just merging those two sentences and updating the goal kind of to proving Z is in C. So skipping right over this step, and now this is our goal. So if we prove that Z is in C, then we are done. And this one time only, I'll write some extra concluding sentences after we prove that Z is in C to explain why we're done. But typically, if your writing is clear enough, then you wouldn't need to write those concluding sentences because the reader of your proof is assumed to already understand that, when you write like this, you're doing a universal generalization. And the reader is expected to understand that when you're assuming Z is in A, that's because you want to prove that Z is in C. So I will show you what I mean when we get to the end. Okay, so here I am now, and my goal is to prove that Z is in C. What I have available to use is these two facts. Each of these is actually a universally quantified proposition, right? This one says every element of A is an element of B. This one says every element of B is an element of C. So somehow I need to make use of those facts. To make use of a universally quantified thing, I should use universal instantiation. So that means take a universal statement and apply it to a particular case. So for example, every element of A is an element of B. That seems to apply now, because I have a particular element of A here, Z. So since every element of A is an element of B, and Z is an element of A, we have in particular that Z is an element of B. So that's a universal instantiation there. And you don't see the universal quantifier. I didn't write this anywhere in the proof. But that's because I have this shorter way of writing it. So that's how I want you to think about definitions versus axioms. Definition is just giving you a shorter way to write something. So when you see the definition, you should expand it out in your mind. When you see this, in your mind, expand it out to saying every element of A is an element of B. And the every is that quantifier that's there. Okay, so now we have used this fact. We can now also use this fact because we have an element of B. Every element of B is an element of C. So since every element of B is an element of C, and Z is an element of B, it follows that Z is an element of C. And that was our goal, so we are done. So this would be a perfectly good spot to end the proof. In fact, this box that I'm putting here, the box stands for QED, which is abbreviation of a Latin phrase, quod erat demonstratum, which means that which we set out to prove has been proven. Something like that. So this sort of is a stand-in for all the concluding sentences, but let me just fill in the concluding sentences this one time so you see what I mean. So since we assumed that Z is in A and proved that Z is in C, we get this. Since Z was arbitrary, we have for all Z, Z in A implies Z in C. And why am I writing it like this? I have a shorter way of writing that. Like that. So that would be the end of the universal generalization. So this is a little bit difficult to process the way this is organized with the way I merged these two sentences here. So let me just temporarily unmerge them. Originally this said consider any Z, and then we said assume Z is in A, right? And we had these as two sentences. Then here's what's going on. We start a universal generalization here. So this is the start of UG. And then we end the universal generalization here. And this is the conclusion of the universal generalization. And we started, let me use a different color, we started the proof of an implication here, and we ended that there, and this is the conclusion of the proof of that implication. Right, to prove an implication, assume the hypothesis, that was the first step, and then get the conclusion. There's the conclusion. But because of the way people merge these two first sentences here, you sort of don't see all that, and in the end you're better off just not putting the concluding sentence and just having a clean enough and organized enough proof that it's clear when you're really done. So let me fix it and re-merge those two sentences. Consider any z in A, and then I would say, don't put this junk here. Do this instead. And if this can get confusing sometimes. If you have a lot of different components, you have a long proof sometimes, and you have a lot of different components that you're trying to establish. To make it clear which ones have been established, you can put concluding sentences to say like, oh, therefore we have now proven this or that. That's a very good thing to do. Another way to make it clear is to divide up your proof into individual claims, or to split it up into multiple theorems that are referencing each other. So you'll see plenty of that as we move along. So one thing I also want you to pay attention to is the fact that I did not include the scratch work here in the proof. So your goal is to write kind of a perfect, beautiful, nice proof that's clear and easy to understand, but that doesn't contain any of the ugly stuff that you had to think about in order to come up with the proof. So people are usually not used to this in Math 8, since in previous courses you're told, show your work, so you can get partial credit. Here, now that we're writing proofs, and for the rest of your proof writing, all the proof-based courses that you might take, the advice is different. Don't show your work. Show your final proof and make that good. In fact, we don't care about the work. The goal, you in fact want to hide the work. Keep that a secret, and just show this like most cleaned up version of your argument. Usually in the end, when you write a final draft of your proof, it can make you look smarter than you are often. So when you read a proof in a textbook, or when you read my proofs, it's making me look smarter than I really am, because the proof already has everything kind of figured out in my scratch work, and then it's all put in making exactly the right steps in the written final draft. So you want that. You want to look smart in your proof and communicate clearly. So just to clarify that point, by look smart, I don't mean try to confuse the reader. So you still want to communicate as clearly as possible, but you don't necessarily need to lead the reader to show them how you figured out the proof. No one cares how you figured out the proof. Well, your teacher cares, but the reader of your proof, the mythical reader, does not care how you figured out the proof. They just want the proof, so you want to communicate it clearly and convince them, not confuse them. Okay, and before I get off of this topic of transitivity for inclusion, I want to show you, just quickly, another one of these beginner Math 8 mistakes that happen. This happened basically every quarter that I've taught Math 8. Tons of people make this mistake. So, while inclusion is transitive, membership is not. So what I mean is, this thing that I'm saying here would not work for the membership symbol. It does not work. It's tempting to say, well, if I have a bag of stuff called A, and this bag of stuff contains another bag of stuff called X, and that bag of stuff contains a little item called y, well, then in this picture you have y is in x and x is in a. So it's tempting to say, oh, so then y is in a, right? It's tempting to say that because, in the mental image, it looks like y is in a, right? Here's a, it's this bag, and y is somewhere in there, physically, in the mental image here. But this is where the mental image breaks down. That is not what membership means. So the way membership is designed, it's not transitive. And when you look at, going back here to Axiom 5, when you get some experience with using Axiom 5, you will start to get a feel for what membership is really means, and it will make sense.